Hi guys, it's Kate, and this is the first video for, well, it's technically 3 lectures over 2 weeks, a fortnight, 7, of Math 23B. So this week is quite challenging material. It's going to combine a lot of different topics. It's going to combine functions and integrability, which we've been studying at the start of this semester, and combine it with sequences and analysis, which we studied last semester in October. So the key here is to really bring an eye to the detail. Be clear on every definition. Be clear on how to express yourself correctly using the notation as you're going through these proofs. Understand what's happening at every single point, or at least try to, right? We always strive to do that, but with some types of mathematics, it's an acceptable method to say, you know what, I'm just going to do a couple of examples and see how that works out. With analysis, it's very difficult to jump into examples without really appreciating things on a detailed level. So really try to ask a lot of questions, be nitpicky with yourself, go through everything with a fine-tooth comb. Okay, here we go. We're going to be discussing sequences of functions now, so we're going to first talk about interchanging limits and integration. Now imagine that you had a sequence of functions. In general, we denote sequences of functions as f sub k of x. They're functions of x. Their index number in this sequence is k. So this is really like f sub 1 of x is the first function, f sub 2 of x is the second function, f sub 3 of x is the third function, and it's a list of these functions. And what do these functions look like? Well, note that k is an integer, and the function will equal 1 on the interval from k minus 1 to k, and then it's 0 everywhere else. So that means that f sub 1 of x, that's going to equal 1 from 0 to 1 and 0 everywhere else. And f sub 2 of x is going to equal 1 from 1 to 2 and 0 everywhere else. So these are discontinuous functions. Now it says clearly the integral from 0 to positive infinity of f sub k of x dx equals 1 for any k, right? It just looks like this. It just looks like this depending on what k happens to be, and that area under the curve where it's non-zero is always going to be equal to 1. So for every single integral of f sub k from 0 to infinity, no matter what the k happens to be, it's going to evaluate to 1. But that means that if we take the limit as k goes to infinity of these integrals, right? If these integrals are always equal to 1, that means their limit is also going to be equal to 1, right? If you were taking the limit of these integrals of f sub 1's integral, that's 1, f sub 2's is 1, f sub 3's is 1, f sub 4's is 1, that sequence of the values of those integrals is always going to be 1, and so the limit is going to be 1, since every element in the sequence is equal to 1. Now what's interesting is that this sequence converges pointwise to the function f of x that is 0 everywhere. So it converges pointwise to the 0 function. And what does that mean? That means that if you're looking at a particular x value, a particular input, the limit as k goes to infinity of f sub k of x equals 0. Right? Eventually, yes, for a moment, the function will be 1 on that interval, but it will be 0 forever after. So pointwise, the function for a particular x value has a limit of 0. So that means that f of x, this 0 function, is what we call the limit function of the f sub k's. If we take k to infinity, what we're approaching at every single point, right, is 0 as a function value. And since f of x is 0, that means the integral from 0 to infinity for f of x is going to be 0, because you integrate 0 over any interval, and you're going to get 0. And note that we have a very interesting notion happening here. If we take the integral of the limit of the f sub k's, we get 0. But if we take the limit of the integrals of the f sub k's, we get 1, right? On this left-hand side of that equality, we are taking the integral of the 0 function. But on the right-hand side of that inequality, I should say non-equality, not inequality. But on the right-hand side, what we're doing is we're taking the limit as k goes to infinity of an infinite sequence of 1s. So that left-hand side evaluates to 0, that right-hand side evaluates to 1. That seems weird. It seems like there shouldn't be a difference whether we're looking at the limit of the integrals of these functions or the integral of the limit of these functions. And so the big question that we're going to start asking for ourselves is, when can we know that the integral of the limit function for these f sub k's, right? In this case, that would have been our 0 function, f of x, is equal to the limit of the integrals of the f sub k's. For us, in this particular example, that was each of those integrals that was equal to 1. When can we be sure that those are actually equivalent? What would we need to know about these functions, or what types of functions would we need to be working with in our sequence? And so our answer for this right off the bat is that for Riemann integrals, there are 2 requirements. Both of them actually happen to be violated in this example. One is that there must be a bounded region outside of which all of the f sub k's are equal to 0. And that doesn't exist. There is no place where every single f sub k is equal to 0, because eventually, and note that we're talking about on our interval is going from 0 to infinity. Eventually, the function value at a particular x value, input value, will be 1 for one of those f sub k's. It will happen only one time, but what that's doing is that there is no bounded region outside of which all of the f sub k's are equal to 0. Because every single f sub k has a different bounded region where it's equal to 1. And none of them overlap, right, except for at a singularity, but it's not like you take the infinite number of them and you can find where the bounded region where the f sub k's are not equal to 0, and then outside of that, that's where they're equal to 0. So that's what's really breaking down here. And then the other thing is that the f sub k's must converge uniformly to f. And this is a definition that you certainly need to know, just like you knew the definition of continuity and convergence backwards and forwards. Now, what does it mean to converge uniformly? This means that for any epsilon greater than 0, right, for all epsilon greater than 0, there's going to be some index k where you can look at the functions that come after this index, right? You look at every single function that comes after this big K, and you say, for every x in Rn, their function value for all of these functions after big K is within epsilon of their function value in the limit function, right? F of x. Now, how is this broken down by this particular example? Well, if you pick any epsilon less than 1, right, and we're trying to find some big K that says, hey, after this big K, every single function that comes after big K has the property that the function value of f sub k of x is within epsilon of the function value of f of x. Well, that breaks down, right? Because if we pick an epsilon that is 1/2 or 3/4 or 1/4, there is nowhere that I can point to in this list of functions and say, beyond here, every single function after this, the function values across the board for all x's are within 1/2 or 3/4 or what have you of the limit function, which is 0, because in each of those f sub k functions, there's going to be that interval where the function value is 1. Let me repeat that very carefully. We do not have uniform convergence in this example because there's always an interval in every single one of the f sub k's where the function value is 1 and our limit function is the 0 function. And so there's no way to say, hey, for that interval where the function value is 1, we're within epsilon, of the limit function because 1 is not 0, and we can't even squeeze it to 0, right? For that interval where the function's 1, we can't pull the function values for those inputs towards the limit function. And that's true for every single k. There's always this interval where the function's equal to 1, the limit function is 0 everywhere, and we can't get any f sub k within epsilon of f of x across all the values for x. In this particular case, you pick any k, and we say, okay, epsilon is 1/3. Well, from k minus 1 to k, the function value is 1, and it breaks that epsilon. When you say epsilon is 1/4, from k minus 1 to k, the function value is 1, and it breaks that epsilon because in the limit, this function is everywhere 0. So work through that, think through that, make sure that's clear to you what's going on there. Just as a review, we're going to be using a lot of what we learned about with Cauchy sequences and sequences in general in the fall semester, again, in this section of the course. So just a reminder for what Cauchy is. If you have a Cauchy sequence whose terms are denoted a sub I, that means that for any epsilon greater than 0, we can choose an index such that for any two terms that come beyond that index in the sequence, the difference between them will be less than epsilon, or I should say the distance between them should be less than epsilon, will be less than epsilon. We also note that we learned that every convergence sequence is also a Cauchy sequence, and every Cauchy sequence of real numbers is convergent. You guys learned how to prove that, and you also learned how to prove that every Cauchy sequence is bounded. So these 4 bullet points and the value of knowing all of the different idiosyncrasies of Cauchy sequences is extremely valuable as we're looking at sequences of functions.